not do that one. Page 9, number 17. Okay, so our function f needs to be continuous, which means f of negative 2 needs to equal what? Not the answer, but the two-sided limit. Okay, so if it's continuous, then f of negative 2 needs to equal the two-sided limit. So can I just do a direct substitution here? No. So what do? Factor it. We can't do direct substitution. Another option is that we factor and reduce. Because by factoring and reducing, we are getting rid of the whole, but it can still have a two-sided limit. So that's why it's okay to do this. So we factor, we reduce. Now we can direct substitute in, and we get 4. The two-sided, negative 4, sorry. The two-sided limit is negative 4, so the function value has to equal negative 4 in order for this to be continuous. Okay? Let's go back and look at number 15 now. I have a piecewise defined function. For what values of x is f not continuous? Now, where do I need to look in this piecewise defined function? Well, first of all, it's a multiple choice question, right? So 0, 1, and 2 appears to be where I need to look because those are the only answer choices I have. And so those are where these rules are changing. Okay? If this was a free response question, you'd also want to look at the individual rules. Are they continuous everywhere? Is sign continuous everywhere? Yes. Polynomials are continuous everywhere. So that's not an issue. It's also not an issue because all the answers are here. So that's where I need to look. So I'll look at one of them with you. Let's look at 0. Okay, so in order for it to be continuous at 0, I need to find f of 0. F of 0, so which rule do I use? The first one or the second one? The second one. And I get 0 squared, which is 0, needs to equal the two-sided limit. So first I need to see if there is a two-sided limit. So the limit as x approaches 0 from the left, that's going to be this rule. Does that equal, I'm not sure, the limit as x approaches 0 from the right? And that would be the second rule. I plug in 0 here. The sign of 0 is? It's one of the two. Is it 0 or 1? It's 0. It's the y value. Think unit circle. It's 0. 0 squared is 0. So do I have a two-sided limit? Yes. So the limit as x approaches 0 of f of x is 0, which is also my function value. Okay, so I have my three things. The function value exists, the two-sided limit exists, and they're the same thing. So it is continuous at 0. So it is not any of the answers with 0 in them. Okay, so for the sake of time, let's look at the answer that it is, which is 2. But I mean, normally you'd have to look at all of them. Well, let's go ahead and skip fast forward and look at 2. So f of 2, I'm going to use which of the 4 rules for that? The third one, because that's where it's equal to. And I get 2 minus 2 is 0. And then we're going to look at the two-sided limit. The limit as x approaches 2 from the left is 2 minus x. And we don't know, does that equal the limit as x approaches 2 from the right, which is x minus 3. We do direct substitution, and we get 0. And over here we get negative 1. They are not equal. It is not continuous at x equals 2. Okay, so that's what that would look like. Yes, ma'am? Oh, yeah, I guess it is. Because you shouldn't use both of them. Yep, that's a typo. Thank you. Okay, So next, I want to look at a free response question. So turn to page 15, problem number 26. This is an actual free response question from 2012. We are just going to work one part of it because that's the part pertaining to this topic. I'm going to give you 2 minutes. Remember, for it to be continuous, you have to show 3 things. If you're not sure what those 3 things are, it's at the beginning of page 1 of your packet. Okay, the 3 things that we need to show or show aren't true in order to determine if this is continuous are the function value has to exist, so g of -3. So for that, we're going to use the first function rule. So g of -3 is going to be f of 3. So we plug that in up there, and we get 4. So yes, we can check the first thing off our list. Our function value exists. Next, we have to show the 2-sided limit exists. So the limit as x approaches -3 from the left. That is going to be this rule. Does that equal? We don't know yet. The limit as x approaches -3 from the right. That's going to be our other rule. We already plugged in -3 here, and we got 4. Oops, I didn't put a -3 here, did I? We get the same answer, but I left the negatives off. We plug in -3 here, and we get 4. So do we have a 2-sided limit? Yes, and it equals 4. Okay, so finally we need to show that the function value equals the 2-sided limit, and so g of x is continuous at x equals 4. Now, I'm going to show you the rubric for this part of the question, and then we're going to look at some samples. No, that's not correct. At x equals -3. Sorry, the answer is 4. So I'm going to turn and look at the rubric, which you have on the next page, but let's stay on your page so you can look at what you wrote and evaluate what you would have scored. So on the rubric, if you've never seen a rubric, over here you're going to have some work, which is not necessarily the only correct way to write it, but it's one correct way to write the answer. Over here is the scoring. This part was worth 2 points. 1 point for this, 1 point for this. Okay, so you get a point for considering the one-sided limits. Whether or not you do anything with that, or whether or not you get the correct answer, does not matter. For considering the one-sided limits, you get a point. So here they have the limit as x approaches -3 from the right, and the limit left, sorry. They both look right to me. One should be left and one should be right, but they both look the same here. Equals the limit as x approaches -3 from the right. Oh, never mind. Sorry. Here's the left, here's the right. There we go. They are both pluses. Okay, so they've considered the one-sided limits. You get a point for that. So here's back here on what I wrote. Here's where I considered the one-sided limits, the 2-sided limits from each side. Okay, so I get a point. And then the other point is for the answer with the explanation. Our function is continuous at x equals -3 because, and we have to have all 3 things for this. Okay, our 2-sided limit exists. our function value exists, and they are equal. We've got to have all three of those parts for this other answer point. Okay? So turn the page to 16 and you'll see this rubric. And then on 17 is sample A. So this is an actual student sample. So let's read it over. Just the part C, don't read the D at the bottom. And look at the rubric. And I want you to try to decide if they get the 2 points. Okay, they get the first point, or do they get the first point? The first point is awarded for considering each of the one-sided limits. Do they do that? Yes. Here and here. Now, did they drop their notation here? Yeah, they do. They drop this negative, and over here they drop the positive, which is incorrect. They should continue that notation, but it doesn't matter. They considered the one-sided limits. They get the first point. The second point is for concluding that it is continuous and showing all three parts. Okay? So, I'm going to stand right here. Have they done that with what's shown over here? No. Okay? They haven't shown that we have a two-sided limit, and they haven't shown that it equals the function value in just this work. But they have shown it by this. Is it the most precise notation? No, it's not. Okay? But it's all in there. G is continuous at x equals 3. The left and right hand limits as x approaches negative 3 are both equal. Okay? I have a two-sided limit. And it equals the function value. Okay? And over here they found the function value. That's the third thing. They've got it all in there. Is it necessarily written out the most precise way? No. But it's all in there. They get this point. Okay? Let's turn the page and look at sample B. Okay, do you think they get the point for looking at the one-sided limits? Okay, and this is a tough one. And this is why I want to look at these samples. They don't show the correct, the positive and negative signs here. They've left that off. But they've plugged in the correct function rules. So they gave this to them. They did. They gave them the point for this. But is that something I'd count off for in my classroom? Absolutely. And can you bank on them giving you the points for that? I don't know. But that's what they decided to award for this. They awarded them a point for looking at the one-sided limits. They did. Okay? What about the second point? Have they found the three things? I mean, I know it's hard to read. Some of it's off the page, but let's see. They're saying here something about the two functions that meet at x equals negative 3, something about them having the same values. Which, I mean, I think that's what they're talking about over here, right? But do we have two functions meeting at negative 3? I mean, really, it's just one function that has pieces. And they really haven't said that we have a two-sided limit, that this is not enough to get them the point for that. And then they also don't say anything about the function value. Okay? Oh, well, they do say the two limits are the same right here. Sorry. They do say that, but they don't say anything about the function value equaling the two-sided limits. They're missing two of the three pieces for this. So they absolutely do not get that point. They did, though, give them the point for this. So I think that's interesting and something that we should note. Okay? Let's look at sample C now. Do they have the two-sided limits? The two one-sided limits? Yes. And it's beautiful. Okay? Let's read the rest of it. Decide if they have the three things they need to show continuity. What do you think? Did they get the second point? No. Okay. They have their two-sided limit. They've got that. And they say that it equals the function value, but they never told you what the function value was. All they had to do was say this. 4, right? Yes. That's all they had to do to get the point. It's beautiful, but lacking. Okay? You've got to put that in there. Are you going to get points for arithmetic, like actually calculating these things? No. I mean, they didn't do any arithmetic up here. You don't get any points for arithmetic, but they had to state this, and they didn't. One more, and then we're going to move on. D. Okay. Do they get the point for looking at the one-sided limits? No. Is that what they're doing? Yeah, it is. But they don't use limit statements. No. And since they don't have, there's nothing in here about limit statements. No, they get nothing. Okay? Is this the arithmetic that's going to go on in order to get this, to show that we have a two-sided limit? Yeah, it is. But they use no limit statements. They get no points. Okay, so hopefully we can learn a little bit about that and about how we need to make sure that we state things correctly in free response questions. Oops. Okay. So let's go on now and talk about differentiability. Okay, and again, I think the easiest way to talk about how we know whether or not something is differentiable is to talk about how we know something is not differentiable. So a function is not differentiable if there are three things. What three things destroy differentiability? Sharp turn, a hole, so it has to be continuous, and vertical asymptotes. Okay, awesome. So this is not on there anywhere, so you might want to make yourself a note right there on page 1 or 2 where we were just looking at these things. The three things that destroy differentiability. Sharp turns, cusp, corners, those are all the same thing. Okay? That's all the same thing. Continuity, it's got to be continuous, so if it's not continuous, which is a hole or any other point of discontinuity, and vertical asymptotes. Or actually, that would be discontinuity, wouldn't it? This is supposed to say vertical tangent lines. Vertical tangent lines. Which was illustrated in that picture on page 2, where I have something that gets very vertical, like that. Vertical tangent lines. Okay. So let's look at a couple of multiple choice questions. On page 10, question number 19. Here's a nice pretty picture. What values of x is f continuous but not differentiable? Okay, so is it continuous at A? Yes. So that means the first part of it. Is it differentiable at A? No. Sharp turn. There's my answer. Okay, but let's go ahead and look at the rest of them and why they're not answers. At B, is it continuous? No, so it doesn't meet the first requirement. This is not continuous. What's wrong at C? It's continuous and differentiable. It's both, and it didn't want it to be differentiable. So this is both. The derivative is about 0. Okay, what about at D? Not continuous. So if it's not continuous, it can't be differentiable. And E is continuous and differentiable again. Okay? Okay, let's look at 14. Okay, so here's a Roman numeral problem. But in fact, they depend on each other. One being true, if 1 is true, then that's part of the conditions we need for 2 to be true. And if 2 is true, that's one of the conditions for 3 to be true, right? So let's start off with number 1. F has a limit at x equals 2. In order for f to have a limit at x equals 2, what do we need to look at? The right and left hand limit need to be the same. Now, let's look at this. Do I actually have to calculate 2 limits here? No, because the function is this to the left of 2 and to the right of 2. This is my function rule. So I only have to do it once. My 2-sided limit is going to be the same. If it exists. Let's put it that way. So can I do direct substitution here? No, so I need to factor. Good, factor. And we get so our answer is 4. So do we have a limit at x equals 2? Yes. So that's true. So eliminate choices B and C, because they don't include Roman numeral 1. Okay, in order for it to be continuous, I need 3 things. I've already showed one of them. I need a 2-sided limit. I've got that. That's the second part of being continuous. What's the first part of being continuous? Okay, the function value has to exist. And it does. F of 2 is 1. So that's the first part. The second part of continuity is I have to have a 2-sided limit. And I've got that. But the third part is those 2 values are supposed to be the same. And they are not. So this function is not continuous. So Roman numeral 2 is not true. So this is false. Now, that narrows down my answer to A. But what if one of my answer choices was 1 and 3? Do I need to look at that? No. Because if the function is not continuous, it's not differentiable. Okay? It couldn't be 1 and 3. Because being continuous is a condition of being differentiable. Okay, let's look at another free response question. Let's go to page 13 and look at problem number 24. Okay, 3 things. Function value was 2. 2-sided limit, they were both 2, so we have a 2-sided limit. and it equals the function value, so our function is continuous at x equals 3. Okay, the limit as x approaches 1 from the left, okay, is 1. Awesome. The limit as x approaches 1 from the right is 2. So it doesn't matter what the function value is. It matters what we're getting closer and closer and closer to. So the two-sided limit is 1.5. Good. You didn't fall for that. It does not exist. They have to be the same thing in order for us to have a two-sided limit. Okay, then below that, we have a similar problem, but not a graph. We have function rules. So take a minute to look at this. We have a piecewise function rule. So our question asks us about a two-sided limit. Okay, so we need to find the two-sided limit. So we need to find the limit as x approaches pi over 4 from the left. We're going to look at the limit as x approaches pi over 4 from the right. Okay, so from the left, which piece of this piecewise function are we going to use? Sine. Good. And so the sine of pi over 4 is square root 2 over 2. Okay. From the right, the limit as x approaches pi over 4 from the right, we're going to use cosine. And the cosine of pi over 4 is square root 2 over 2. Okay. Now, what I want to point out here, though, is if I plug it into the third rule, because I've seen papers, and somebody's going to do this. They're just going to evaluate all three rules. And we get to the tangent of pi over 4 is 1. Okay? So is the question, or is the answer 1? Is it square root 2 over 2? Or is it does not exist, because all three of these did not have the same answer? Okay, and the answer is this. This is the answer. I don't need to do this. This is not needed. In order to have a limit, I need to have the limit as x approaches from the left equal the limit as x approaches from the right. It doesn't matter what the function rule is. If I graph this, I'm approaching this number from the left. I'm approaching square root 2 over 2 from the right. The function value is 1. It doesn't matter. This is the limit. Okay, did you have a question, sir?
Me?
Yeah.
Oh, no.
Okay, I just couldn't hear what you were saying. Okay, we good? Okay, so let's go work some questions from your white packet. Starting on page 9, I want you to work questions 18, 20, and 21. And I'm going to give you about 2 minutes to work by yourself. Questions 18, 20, and 21. Take a look at those. So here's the graph of f. Which of the following statements of f is true? We take a look. Our statements have to do with the function as x approaches a and as x approaches b. They're all two-sided limits. None of them are one-sided limits. So we look at the limit as x approaches a. From the left is 2. From the right is 2. So the two-sided limit is 2, and that's the answer. Okay, but let's go ahead and look at b and why none of the other answers are correct. So the limit as x approaches b from the left is 2, and the limit as x approaches b from the right is 1. So there is not a two-sided limit for b, and that's not an answer choice. Here it says it's 2, nope. 1, nope. Here it says it's equal to this one. It doesn't exist. Okay? Awesome. Let's look at 20. If we look at 20, we have 3 different graphs. And it says, for which of the following does the limit as x approaches 4 of f of x exist? And so it can be more than one of them. So we have to look at all 4. So we look at this first graph, and we have this limit as x approaches 4 from the left, and the limit as x approaches 4 from the right is existing. It equals whatever this is, like 3-ish. Okay, so that's true. It could be 1. Okay, so it can't be answer choice B or C because they don't list 1 as being an answer choice. Next, we look at 2. We have the limit from the left and the limit from the right, and they equal the same number. Again, whatever that is, it doesn't matter what the value is. So 2 is also true. So now it can't be this one because it doesn't include 2. And it can't be this one because 2 is not included. So my answer is D. So let's look and make sure that 3 does not have a two-sided limit. So the limit as I approach it from the left is 4, and the limit as I approach it from the right is about 2. So no, this does not have a two-sided limit. Problem 21, just ask us about the left, right, and does it have a two-sided limit? So does the limit as x approaches 2 from the left exist? Yes. Do I know what it is? No, it doesn't matter. It does exist. This is true. Does the limit as x approaches 2 from the right exist? Yes. Are they the same thing? No. Okay, so again, it's Roman numeral 1 and 2. Okay, with the Roman numeral problems, you gotta look at everything. But if you only know one of them, like for instance, you weren't sure about this, then you can definitely eliminate some answer choices to help you have a better chance of guessing. Okay, awesome. So we looked at the limit as x approaches a certain value. We looked at the limit at a point, approaching a number. Now let's look at the limits at infinity. Okay, so this is on our blue packet on page 2. So what we mean by the limits at infinity is we're looking at what happens to our function as we go to infinity, either positive or negative. So what is happening way out there? What are we going to find way out yonder, this way or that way? What information are we going to get from this? We're going to find horizontal asymptotes. Okay? This gives us or tells us horizontal asymptotes. So what I have here is the rational function theorem, and this is what we're going to use to figure this out most of the time. Now, not all of the functions that we're going to look at for limits of infinity are going to involve polynomials, which is what this rule applies to. But this is going to help us solve most of the problems. So when we're looking at the limit as x approaches positive or negative infinity, we want to look at the degree of our polynomials. If the degree of p of x, our numerator, is less than q of x, so let's think of an example of that. So an example of that is if x over x squared. This degree is 1, this degree is 2, so the degree of the numerator is less than the degree of the denominator. Now let's think about what's happening. I'm just going to pick positive infinity. So let's think about what's happening way out to the left. X is going to infinity. It's pointed up. This is getting really, really, really big in a positive direction. Okay? X squared is also, here's y equals x squared. It's also going up without bound to the right. So it's going to positive infinity. Okay? So just thinking about that separately tells me nothing. But here's what's happening. This has a bigger degree, so this is getting bigger faster. So this number, as I go way out yonder, is always going to be bigger than this number. So my limit is approaching infinity because this one's getting bigger faster. Well, if I flip-flop it, what? This is going to infinity and this is going to infinity, so sorry. Let me say it again then. This is getting bigger faster, so if I'm dividing by a bigger number, then it's approaching 0. I may have said infinity, but what I meant is 0 what I wrote. Thank you for correcting me. Okay, so now if I flip-flop this, and I have the degree of the numerator being bigger than the degree of the denominator, again, they're both going to infinity, but this one is getting bigger faster, so my numerator is bigger than my denominator, then this is going to be positive or negative infinity. In this case, it's positive infinity, but we'll look at a problem and see how we decide about the sign. Okay? Now, if the degree of both of them is the same, then they're both getting big at the same rate, then I take the leading coefficients. And that's what my limit is approaching. Okay, so right below that, you have 4 problems. So let's take a look at these. Now, in all these problems, we're going to infinity or negative infinity. So that's what signals to me that I'm going to want to use this theorem. I'm looking way out there. So I only need to look at the highest degree. So I'm not even going to look at the rest of this problem. I have 2x over 5x to the 4th. So the degree of my, which is bigger? Denominator is bigger. So this is getting bigger faster. So I'm dividing by a bigger number. So this is going to 0. Okay? If I look at example 2, be careful because it doesn't have to be your first term that is your highest degree. In this case, it's 2x to the 4th. My highest degree down here term is 5x to the 4th, so they're the same. So this is going to go to 2/5 because they're both getting big at the same rate, so I look at the coefficients. Now, in these last 2 problems, I have the same function. I just want to go to positive infinity or negative infinity. And in both of these cases, the degree of the numerator is bigger than the degree of the denominator. So the numerator is getting bigger faster than the denominator. So they're both getting really, really, really big. So both of these are going to have something to do with infinity. And I need to decide, is it positive or negative? They could both be the same, or they could both be different. So here's what we need to look at. We need to fall back on and remember some stuff we've already learned. This is one of the biggest things that some of my students struggle with, is they think that they don't get to use what they learned in Algebra 2 and Pre-Cal. But you've got to use that stuff here. X to the 5th. Okay? Tell me something you know about the ends of x to the 5th. We're talking about the ends here. Okay? The ends look like this. Yes? If this power is odd, the ends are going in opposite direction. And if the function is, this term is positive, which it is, then it's going up on this end and down on this end, right? And if this was negative 2x to the 5th, we would reflect that, okay? I don't care what's going on in here. I'm talking about the ends here. So the ends look like this. So this numerator is going to positive infinity. It's going up without bound, okay? Over here, now I'm going to negative infinity. So my numerator is going to negative infinity, okay? Because as I go to negative infinity, my tail is pointing down over here, right? So I'm getting really, really, really big in a negative direction. Now let's go back and talk about the denominator. I have x to the 4th. Well, when my power is even, my tails are pointing in the same direction. They're either both going up, in this case, because it's positive, or if it's negative, they're both opening down. So they're both going up. So this is going to positive infinity. And over here, my denominator, because it's an even power, is also going to positive infinity. Okay? So I have a really big positive number divided by a really big positive number. So my answer is positive. And again, it was infinity because this is getting bigger than this. So the numerator is bigger. Over here, I have a really big negative number divided by a really big positive number. So my answer is a really big negative number. Okay? So the sign changed because I was going a different direction.